predicting sort of, you're assuming that error due to local gravity change in your measurement?
No, this I don't know. We did some accurate measurement for the path, but I don't know about the effect of gravity on the clock.
Mm-hmm. So in, for example, technique that we use in lunar laser ranging, we use a normal point for each pulse. We send 10 to the 10 to the 18th photons to the moon. We get 1 photon back every 100 pulses. So, but we form a normal point, and we describe each normal point. When we get a signal back on Earth, we describe and provide statistical characterization of each pulse. I would like to see statistical characterization for each event you have. And that would probably be similar to the question, different pulse weights and different sort of events that you consider into one pulse. So I think it would be nice to see this data announced as well.
So thank you very much for the nice presentation. I have 2 questions. One is very short. Maybe I did lose one point. You use a muon, you produce a muon neutrino, is it right?
Yes.
And you also reveal a muon neutrino.
Yes.
So oscillation don't play a role probably in the measurement. Is it right?
Okay.
Okay. The second question is about the calculation of the error. I see you have about a dozen sources of systematical error.
Fortunately, yes.
Yeah, and you sum them in quadrature. And I know there is some people which would say that you should sum them linearly.
Yes, but some other people said that if they occur from if each error is independent and not correlated, then you are allowed to sum them up in quadrature.
Yeah, that was right the point. I was thinking you could assure me that the systematical errors are not correlated, or I mean, are of some statistical origin, like from Monte Carlo simulation or something like that. So you have the complete right to sum in quadrature.
I mean, most of the delay are simply due to most of the effects are due to delay in some devices. So measuring different devices with a different analysis technique, it's unlikely that you do something which is correlated. And then furthermore, suppose that we miss a delay. Then this will increase the delta t. It will not decrease it. So any delay we miss will make the neutrino faster.
Okay, maybe I missed this point, but so you're combining data from 2009, 2010, and 2011,
yes.
Right? Can you also show, maybe, I think you had a plot in which you have separate results for the 3 different years. Okay, so is there of course, I mean, they are compatible, but is there a particular reason why, for example, in 2010 they're both below the mean, and in 2011 they're both above? So is there like some hidden reason why there should be this, or I mean, is it fair to combine them?
I think
as if they were,
it is fair. I mean, if you perform some numerical test, very likely you will end up saying that this is a flat distribution.
Sorry, I wonder whether you are worried. I mean, to give the result, you are buying some uncertainties from external sources like this geodesy campaign, GPS. So, are you worried about this in the sense? It's something that you cannot test. You are just to.
So just to tell you something about geodesy. So the geodesy error is 20 centimeters, and the geodesy people are completely disgusted by this huge error. They would like to make a measurement less than 1 centimeter. But the problem is that we have to close the highway on both sides of the tunnel for all the time needed by the geodesy people to do very accurate measurement and propagate the reference point inside. I mean, we cannot close the highway because we will block interconnection between the east and the west part of Italy. So they have to do something rather rough, but for them it's disgusting. And so
But what about the GPS?
we are safe. But for the GPS, I mean, what I told you, we asked to the Swiss. They did whatever they could at their best. I mean, they are not the first Swiss that crossed the street. I mean, they did also something for the US Naval Observatory, so it is not the first time they are doing this sort of measurement. And then we asked to the German to check what the Swiss did. But, I mean, this is not something we can check on our own. We trust those people. And it's a different experiment. It's not like we are using only the Opera data to do something with our own data. We need input from experts, and we try to find the best expert available. And whenever possible, use two experts and try to compare the measurement. I think this is the best we can do.
My question is very closely related to the last by Paolo. So this is a very naive question. So these experts you were mentioning about, I mean, in their expertise, is this nanosecond error range crucial in some other area of research or of technology? Or, I mean, this nanosecond time...
Yes, this is what I told. Maybe I was fast, sorry, but... There is this field called high accuracy time transfer. And this is used for them. For them, it's standard.
No, let me say another way. Let's assume that by some coincidence, both the Swiss and the German system have a large systematic error of order, I don't know, 50 nanoseconds, right? That would spoil your measurement. Is this somehow ruled out by some, if this is true, some technique like this one would be, say, I mean, is this ruled out by some other technology or some other thing, or is still a possibility?
The delta T we observe is relatively large, so it's somewhat unlikely that they make such a big error with this in it.
But if they do, what is, say, a practical consequence that this is going to? How can we rule out this? I mean, some.
It's difficult. I will have to think. But it is a good point. I mean, we rely on some other measurement that come from expert people.
Is all the work based, I mean, is all the space geodesy that has been done based on just the contribution of one single team?
The team that did the analysis is a single team, but the measurement that they use are a set of measurements taken by different people. More or less, what they like to do is that they like to measure at a different place in different time by different people, and then they merge everything and they tell you the position of this point. This is what they do.
I understand you're not space geodesists, but the resolving power that we reach in space geodesy is of the order of millimeters per year, or millimeters
yes,
in terms
but
of. Therefore, it's not
I told you that what's.
I mean, if they use permanent stations, I mean, continuous stations in time, they could go down to a millimeter, not to a centimeter.
But the problem is that they are not able to see the satellite from inside the mountain.
Yeah, there are plenty. Geodesy is plenty of you have many onions in the issue. You have the atmosphere, the ionosphere, and the transients in the Earth, and so on and so forth. Therefore, I was just wondering whether you have really a multidisciplinary team that cares about all these different aspects.
No, I mean, the work has been done very carefully by a good team, and the precise measurement at both sides of the tunnel, they are really high precision with a range of precision you are measuring. But you are mentioning. But the problem is when we take the measurement inside the mountain, that's because we cannot close the highway tunnel. They had to do something which is less accurate than what they would like to do, and this is why they end up with this disgusting for them error of 20 centimeters. But for us, an error of 1 meter would have been sufficient. So it's 5 times smaller what we ask them.
I have 2 questions. One is more technical, and it's, well, I'm more confident on your length measurements because I don't think that GPS can make an error as big as 20 centimeters out of 700 kilometers, otherwise we would have major problems than the speed of the neutrinos in our common life. I'm much more suspicious concerning the time measurement. In the sense, I didn't even understand very well, neither reading the paper nor from the presentation I've heard up to now, how do you exactly use this distribution of protons? I mean, you weight at the same way all the points of this distribution, or you give a bit more weight to the rising edge? If you can clarify this point, how do you use
the fit is a global fit. We fit all the distribution is in a single bunch. So we don't give more weight to some particular part of the distribution. This is something we have been asked in particular to repeat the fit using only the leading edge and the trailing edge of the distribution and compare the result to what we get fitting the whole distribution. So these are checks that we got from the community and we are going to implement them.
Yeah, I think there. And the second question is a bit more provocative, but on the other hand also your results is a bit provocative. So as far as I understood, a not, let's say, negligible fraction of your collaboration didn't sign the paper. So this is because they didn't trust the results or because they didn't like the timing and the way?
I mean, what happened in the collaboration is that the discussion was open, and so everyone was left free to choose what was his preferred attitude. And so some of the people decided not to sign the archive paper, and some of the people decided to sign the archive paper. And one of the motivation that led us to go for the archive paper is that in order to get the most solid cross-check of this result, somebody else has to do the measurement. But it's difficult to tell Minos to repeat the measurement without telling them what we found. It's difficult to say to the CERN, stop LHC because we have to do a measurement on the BCT. So you tell the community that you have a potentially interesting result, and you are allowed maybe by this message to do some more cross-check on the validity of your result, and also to alert the community that maybe they can repeat the measurement. So this is what I can tell you.
So I have a question. So when you quote this 6 sigma of statistical error, so this is a sum of many errors, and
yes.
And of course you are assuming that there is a Gaussian distribution there, and I mean, how are you confident that each of the errors which are summing have a roughly Gaussian distribution, that maybe some of these errors cannot have a broad distribution, some tail, and
I mean, what I can tell in this respect is that whenever possible, we have tried to repeat several times the same measurement with different technique. And so we are getting different results. So we are more or less able to check if they are somehow stable. So this gives you a feeling that maybe the assumption of a Gaussian distribution is not completely crazy. Or at least if measuring the same device 2 times, you find a very different measurement, then it's better to measure it a 3rd time with a completely different technique, because you made a mistake the first time. So this is the sort of check we have done on the way the error have been computed.
Okay, so I think we can thank Alessandro for the talk.
Vai, 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 vai tranquilla. Io sono qua, vai tranquilla. Ok.